So let's jump in and talk about the data. So here is the pre-post data that I have for this example. So the way this, you can read this, again, it's about recall, right? So the participant number 1 in the pre-recall task, they were given a list of 50 words, the distractor, and when they were given the recall task, they correctly identified 15. Now, it's possible they may have remembered more, but then also remembered some false words. You know, some words that weren't on the list, some false positives, and that's why the score came down to 15. But in the end, their total recall score was 15 at pre, 13 at post. For number 2, participant number 2 was 20 at pre, 14 at post, and you get the idea. Okay, so what you can see, and I was mentioning before, that oftentimes people that begin high, we start off high, that's funny to say high in this context, but to start off with a high recall score, obviously if they started off high, that'd be a problem, but if they start off with a high recall score, they likely are going to have a high recall score, relatively high recall score. So if you look at, like, this person had one of the highest recalls, and they also were the highest at post. Okay, this person had a high recall at pre, but they dropped down considerably. So the correlation, the dependency between the participants is not perfect, because some people will be more impacted by THC than others, or just the words themselves may be more memorable for other people than others. So here's a person that was pretty high. It's actually the highest person at pre, and at post, they're not anymore. They're not the highest person, but they're still relatively high compared to like a 7 or an 8 or something. They're still, relatively higher than most. So there is going to be a correspondence between where they start and where they end. Often, you're not going to find the person who is the highest often being the lowest, and sort of vice versa. Even though that can happen too, but it's not generally going to be the pattern. So because they're related, and this is the same person here at pre and post, well, I don't have to deal with their pre and post scores. So even though I have a pre-mean, a post-mean, I have their standard deviations and stuff, I'm actually going to expand this out. And because we want to compare the means to see if the mean after is significantly larger than the mean before, we're not going to compare the means, even though I could, right? If I subtract those two means, 17.5 minus 13.9, what is that? It's about 3.4 or something like that. And so I could subtract these out and actually find the difference between them. But it's, what do I do with the two different standard deviations, and how do I go about doing the test if I just subtract the means? I can't do it the way the way I'd like to, and I'll show you sort of why. So we can't perform this test by just subtracting the means. Since scores and the two conditions come from the same people, we can actually subtract the individual scores and create differences like this. So for each person now, I'm looking at their change in recall. Okay, so this person recalled 2 more words in pre than post. This person was 6 more, 1. This person was 11 points higher at pre than they are at post. You get one sort of outlier. It's not an outlier. A person that stands out is that this person number 8 here was the only one to recall more words at post than they did at pre. Okay. But for the most part, there's a pattern that, I said 3.4. It actually looks like 3.6. So there's a pattern where, for the most part, there's at least some positive values here, because people remembered more words, or recalled more words at pre than they did at post. So what we don't get when we actually just subtract the two means is what to do with these two numbers, because I need some form of standard deviation in order to create a standard error. If you remember back to our one sample t, we took the difference between our sample and the population over a standard error, which is the standard deviation divided by the square root of n. So I need to figure out some way of calculating a standard error to do the t-test. And because I have two different standard deviations here, it's sort of, well, what do I do with those? And the answer really is we don't do anything with those. Well, the reason why we're subtracting the scores individually like this is because I want the individual differences so I can figure out how the difference scores actually vary from one another. And the reason for this is it's often pretty common for people to have, for individuals to differ from each other. That's actually not uncommon. However, it's less common for the difference scores to vary quite as much. So if you think about a really goofy example of this is, if I wanted to compare the ages, right? Let's say I wanted to take men, here, instead of men and women, let's say husbands and wives. And I want to do some kind of matched pairs example, where I have a husband here and a wife here, okay? And let's say I have, my hypothesis is something like, I believe that in most relationships, the husbands are older than wives. Right? There's a stereotype, right, that younger women marry older men and older men marry younger women, all that kind of stuff. So let's say I wanted to take a sample of people and see if that seemed to be true. So I look at their ages. So I got a husband comes in, they're 70 years old, and their wife is 68. Okay. Another couple comes in, and the husband's 23, and the wife is also 23. Another couple comes in, and they're 42, and the wife maybe is a year older or something. Then you got another 37 and 34. Maybe you got some big gap somewhere where you got like someone who's 50, and the wife is 23 or something like that. This is the stereotype they're sort of looking into here. And we can continue doing this. And what you're going to notice, right, is that here the variability of people here is going to be, of scores on both of these are going to be large, because people's ages vary quite a lot, right? There's lots of different ages, right? To go from 70 to 23 to 40, lots and lots of variability in ages. However, when you start to subtract to 0, right? -1, 3, and here we got, 27. Now this is sort of the, the non sequitur, but you can see that the difference scores between their ages starts to vary. Like this variance here, this variance is going to be way smaller. Difference scores tend to vary a lot less. So this comes back to the idea that doing a dependent samples test is beneficial, because it helps you to get rid of, to address, to identify some of the random variability between people's scores. Like, people just have differences. People just recall different amounts. Some people have better recall than others. Some people are more practiced at sort of recalling words, so they are able to do it better. Some people have never done that kind of thing before, so they're not very good at it. And you see that where you got, this person only remembered 8 words out of 50. You got somebody else who remembered half of them. Half the words are remembered versus just 8 of them. That's a big difference in just their recall ability. Okay. But when we subtract out and get the difference scores, the variability can be dramatically reduced when they're related. So with dependent samples, because they are related, they're going to be closer together. Right? So no matter where they start, their post is going to be closer to their pre than it is to other people's scores. So when we subtract out the variability of the differences, like this 1 throws everything off, the 11, this one 2, and the 12. But for the most part, people's recalls are actually fairly close, and they don't vary very much. So we go from having a 5.855, at pre, to a 5.377, which is a smaller sort of standard deviation, a smaller variability. So being able to subtract scores like that, it allows us to reduce the random variability between people when looking at their different scores. So by reducing the error, we actually can make the test stronger, right? Because remember, a t-test, generically, a t-test looks like, any t observed is going to be some, like a mean minus population for our one sample test over our standard error, right? Well, if I'm able to, in any way, like take the different scores and use a smaller variance, smaller standard deviation, I can make this thing smaller. If I make standard errors smaller in any way, if I figure out a way to reduce some of the error and make the standard error smaller, well, I'm going to make my t observed bigger. Right? So by making my t observed larger, I've actually now sort of increased, by doing that, I've sort of increased the power of the test. My power to find a significant effect has been increased by simply decreasing, addressing, and getting rid of some of the error variability. So by subtracting and using those different scores, I'm able to use a smaller value here than I would have if I just used the pretest. And this isn't a very stark example of the difference, but it can actually be quite a big difference between, say, a pretest variability and the variability of the different scores. So here's the nice part, the simplifying part of this whole thing. So even if everything I just talked about, that sort of, that went over your head, you don't understand any of this reducing variability part, here's something that's fairly simple to sort of to grasp, which is if I go from pre and post test scores and I subtract them and I get different scores, well, I don't need those pre-post anymore. I can look at the pre-post scores and treat this as just a one sample test. I have my one mean, and I want to compare it to a population value. And you're thinking, well, I said earlier there was no population. Well, not like IQ, where you're given a mean for IQ that you're trying to compare your sample to, but I do have a population value that I'm interested in just generically, which is I'm going to be comparing, this mean of differences to the thing I hypothesized, which is 0. So this is my hypothesized sort of population value, which is if THC doesn't have an impact on recall in the population, I expect the different scores to average out to 0. And that any differences we have here would just be random, but if we sort of averaged over them, you get basically an average of 0 is what I'd be expecting. So this is the value that I'm sort of be comparing to. So this is back to being a one sample test, when I compare my one mean to my population mean of 0, and I have my one standard deviation that I can use to create a standard error and do a t-test. So we now have a single sample problem identical to the one sample test. These are change scores for each person, right? So it's talking about the difference, the change. This person, because it's pre minus post, this person, recalled 2 fewer words. This person recalled 6 fewer words. Now in this case, it may actually make sense to have them be negative numbers, because we're talking about a decrease. So if I wanted to use these as negative numbers, everything would be exactly the same, except this average would be a negative 3.6, but the standard deviation would be the same, and I could test it that way. It just would be reversing the signs of everything, the inequalities, but otherwise it'd be testing the same thing. So you got to know here, this pre minus post means that there was 2 more words recalled at pre than post. 6 more words were recalled at pre than post. Okay, so this actually does represent some, at least some of these people are having issues with recall and recalling more words. There's a pattern of recalling more words at pre than at post. And just to sort of label things, so we're referring to the difference here as D, right? The D for difference. And then if this is then the difference scores, then we're going to use M sub D to refer to the fact that this is the mean of those differences. And then that makes this then the standard deviation of the differences. There's nothing really different, it's not like we're creating something wholly different than the mean standard deviation for a one sample test. Just to differentiate it from the one sample test, these are not just a mean of scores, but the mean of differences, and this is not the standard deviation of scores, but the standard deviation of the differences. So when we go to use our equation, they sort of will line up. So the results, the participants' recall was lower post-THC ingestion. We saw that there was a reduction, but we want to know, was this enough change? Was the recall lower enough for us to believe that THC really was to blame, or could we have got this this difference by chance alone? So before and after scores are not independent. We already talked about that. We already mentioned subjects that were, again, it's funny to use this, but subjects that were high, stayed high, meaning not high on THC, but high. Their recall score was high at the beginning. They actually stayed relatively high at the end. Scores are from the same person, so it's obviously not. So it's not an independent samples, but a dependent samples test. So let's just apply that. If there was no change, right? If we expected if the recall were the same at pre as post and THC had no impact, and and since if we just gave people regular Rice Krispies treats that are just green but had nothing in them, we told them it was THC, to test out the placebo effect, we'd expect the difference to come out to be roughly zero. There'd be no change. So the test to obtain mean difference scores we have, we're calling D here, against the population average, which is based on our null hypothesis that it's zero. Then we're going to use the same one sample test as before, comparing our mean to the population. And again, we don't know sigma. The population standard deviation for different scores of recall is not something that's going to be regularly known or relatively known. So we're going to have to use S, and this is going to be a t-test, not a z. We have the mean of the differences, we have the standard deviation of the differences, or the mean of standard deviations across different scores. Great, we mentioned that before. So we already talked about this too, where we had 10 participants. So our degrees of freedom are 10 minus 1. So we know we have 9 degrees of freedom. Right? We already talked about that when talking about the decision rule earlier. The mean standard deviation we found before. So let's go back and remember what those were. 3.6 and 5.337. So this means this is 3.6. And this down here is 5.337. I think that's what I said a second ago. So just drop that. Yep. Perfect. There's our mean and standard deviation. And the only thing left here is that we know we have 10 subjects. So let's go ahead and fill this in. Let's go to 10. Okay. So notice this. So talked about before, we have S is our standard deviation, and then there's S sub M, which is this is our standard error. Right? This is the standard of the mean, which equals to our S over the square root of N. That's from our one sample test. Okay. So because we're talking about an M sub D, the mean of differences, this is the standard error of the mean of differences. So this is not standard deviation, but the standard error of the mean of the difference scores. So this is still a standard error down here, which is why we're taking that value of S, our standard deviation for the differences, and dividing by the square root of 10, which is our N. So one thing I want to point out here is this is written in this way, this mean of the differences minus mu. Okay, so here is our population value coming in here again. Well, most of the time when doing a dependent samples test, we're looking at different scores. The null hypothesis is oftentimes going to be that there is no difference, or that the difference is zero. The average difference is zero. So oftentimes, because this is often assumed to be zero, right, you often will see this same equation written out a little simplified, where it's like the t for the difference is equal to the mean of the difference over the standard error of that mean of the difference scores. So it's just a mean over standard error. And the reason why this is because every t has got some kind of difference or comparison on the top. The reason why this gets dropped out is because it's sort of implied that this is zero. That the population mean is zero, so they just drop it out because whatever this is minus zero is just the same thing. So you oftentimes will see it without the population mean specified here because it's assumed to be zero. So if you see it this way and you see it this way, it's not two different equations. It's the same equation. It's just this one I'm trying to be a little bit overly specific about the fact we're comparing our mean to the population. It's just we defined our population mean in our null hypothesis as 0. So that's why it's 36 minus 0, which seems sort of goofy, which is why it oftentimes gets dropped out. So 3.6 minus 0, still 3.6. Right? 5.337 divided by the square root of 10 equals 1.688. So this ends up being 1.688 is our standard error. So it ends up being 3.6 divided by 1.688. 3.6 divided by 1.688 equals 2.1327 something or other. 2.13. Okay. 2.133, I think what I said? Yeah, 133. So that is our T for the difference. That is our T observed for the difference scores for this kind of test. Okay. So you walk through the whole thing. We got our mean minus the population mean of 0, which is why it's 3.6 minus 0. We got our standard deviation for the differences divided by the square root of 10 to create our standard error. And we divided our difference, the 3.6, our average difference score, by our standard error, and we got a T of 2.133. I'm going to check something real fast because 5.337 divided by 10 square root equals 1.688. Okay. So that's it. So we have our test statistic, which is 2.133. So that was this whole thing, by the way. This is all, this part of this, when we talk about the hypothesis testing steps, this whole thing is part of step 6, right? The step 6 says, well, now you're going to compute your test. You're going to do your test. And then so step 7 is we're going to compare our test to our decision rule and make a decision. So we have 9 degrees of freedom. Our alpha is 0.05. Our one-tailed T critical we looked up before, but just for the sake of argument, let's just do that again real quick, so why not? We said, all right, we have our one-tailed value here, or one-tailed, level of significance for a one-tailed test up here. So I'm starting with 0.05, which is our alpha level, and I'm going to scroll down to 9 degrees of freedom, which is this 1.833 number. Okay, 1.833 is our critical value. So our T critical is 1.83331 or something like that. That's our T critical value. We calculate our T observed value. So we calculate our T observed. So you can think of this as our either like T observed or T for the difference, right? Is 2.133. 2.133 is our the test we just did. So that's just rehashing our step 6. So then step 7 is where we're gonna compare our values, of T observed or T difference to our T critical, and make a decision. So since 2.133 is larger than, right? It's greater than 1.8331. I'm going to reject the null hypothesis. Remember, the null hypothesis was the one that said if we subtracted the scores and got a difference in our differences, the average of the differences would be less than 0 or equal to 0. So we're now rejecting that. Notice I'm not saying that we're retaining or accepting the alternative, because that's not something we do. We haven't proven that THC reduces recall. But this is evidence to support that idea. So we haven't accepted that the differences are greater than 0 and that there was a change, but we're now rejecting the idea that nothing happened. So something did occur and there's really something going on. So we're rejecting this idea that nothing happened and that there was no change, or the change was in the opposite direction. So here we conclude that the mean number of words recalled after ingestion of THC was less than the mean number of THC before, and this is some evidence that THC does seem to impair recall memory. Okay, that's where this is sort of your decision rule, and then this is more the conclusion that you make because of the decision, and sort of put more into words and back into the context of the experiment with THC and recall and all that stuff. So now we've done all that stuff, let's talk about some advantages and disadvantages here. So I mentioned it before, but one of the things, the big advantages of doing a related independent samples test, and a big reason why people will tend to use it, is because it does help to eliminate some of the subject-to-subject variability. So when people come in and we do a one sample test, any differences between those people we can't explain. They're different. We oftentimes will refer to those as individual differences. They're different, but for reasons we don't know. And because we don't know why they're different, all those differences get sort of folded into the standard deviation and therefore the standard error. It just makes the more people are different, the larger the standard error is going to be. So that's sort of problematic. It controls for some extraneous variables. We oftentimes don't know what the extraneous variables are, but it does tend to control for them. The reason why it does that, like in this case, when we looked at people when they first started, right? We looked at the data here. So there's a bunch of variability here that I can't explain. I don't know why this person here was able to recall half the words that they were shown, and this person only was able to remember 8 of them. Right? That's a big difference in recall. I don't know why, but whatever that is, whatever's driving that difference is being controlled for here, because when we look at pre versus post, it's actually this person was really high on recall the first time. I'm comparing them to their post recall and looking at their change only. So whatever is calling them to be able to recall, whatever is driving them to be able to recall more or less, because I'm comparing them to themselves when it comes to change or the effect that THC is having, all of a sudden it doesn't matter where they start or where they ended. All that matters is how much they changed. So whatever is making them have different recall amounts, recall levels, it's at least addressed to a certain degree, because I don't care how good or bad they are at recall. All I know is how much the recall changes from pre to post. So it helps to address a lot of those often unknown extraneous variables, things that can actually impact the study that you don't know. And so by comparing people to themselves, it helps to address a lot of that. And in general, you're going to need fewer subjects. Now, needing fewer subjects, what does that mean? Fewer subjects relative to the next test we're going to do. We're going to talk about independent samples tests next. And for independent samples tests, you tend to need more subjects to get the same level of power, to be able to say the same thing about the difference. You need more people, because these people are being compared to themselves most often. In the case of matched pairs, this actually isn't true. You oftentimes don't need a lot of people to find the matches. But if you're talking about a repeated measures, you're going to need a lot fewer people, because they're being used as their own controls. So you can get by with a lot less people to do the same kind of study. So what are the disadvantages? And this is, like I said before, this is part of the problem why people don't like to do pre-post tests, and some of the problems with it. So one thing, you have sort of order effects. So an example here of an order effect is that the 2 different lists of words that were used as part of the recall, the order in which those lists were used may have actually impacted their ability to recall them. So for instance, depending on the person's familiarity with the words, the first list could have interfered with the second list and vice versa. And what probably should have happened is that whatever lists were used, they could have been swapped. Some of the participants got list 1 time 1, some of them got list 2 time 1, some of them got list 2 time 2, some of them got list 1 at time 2. So that the actual specific lists that were used at pre to post didn't matter, because everyone got the same list at pre, everyone got the same list at post. There may be an order effect where it's just maybe it's possible that the words were more difficult to recall in list 2. So it had nothing to do with THC at all. It's just they were more complicated words, or they were just less familiar, or whatever it is, that list is actually harder to recall. Then it has nothing to do with THC. It was actually just the order of the list they got that actually can explain the issue. So that has to be sort of addressed. So that's one of the things, is sort of the order effects with anything pre-post or repeated measures. Then you got carryover effects. Carryover effects are probably the biggest issue in pre-post designs. Anytime you do something to somebody, you have them take a test, you have them do whatever, recall, you have them take an IQ test, whatever it is you have them do. By simply having them do that thing, by taking the test, by doing the recall task, whatever it is, it's going to impact their ability to do it the second time. So if I were to give people an IQ test today, and then they take IQ Plus for 10 days and come back in 10 days and take an IQ test, it's likely that by just taking the IQ test the first time, they'll likely do better on the IQ test the second time. Because in those 10 days, they might be thinking about the problems, they may have even gone and like Googled some of the questions to sort of learn information. It's just merely doing the task, taking the test, can actually impact the way that they do the second test. So in this case, like I started to say a minute ago, the fact that they had to memorize 50 words, right? So they remembered 50 words, and they recalled them. And then 2 hours went by. Now they're given a different list. Now it's possible that one of the reasons why they did worse on the second test is because the first list of words they memorized actually interfered with their ability to remember the second list of words. So they may have been recalling some of the original first list words, and that was actually, and they weren't getting credit for those, right? Because you only got 0 points for those words, and it could have actually made it more difficult to recall the new words. There could have been some interference. The reason why it's called carryover, it's for lots of reasons. Literally, stuff could carry over. I always think of if you've ever done like wine tasting, or even like people do like olive oil tasting, all kinds of weird stuff. But anytime you do any kind of tasting, one of the problems you have is that as you taste something, like you drink a glass of wine, the wine that you drink will likely impact the taste of the next wine that you drink. So the taste of whatever wine you start with will actually carry over to the next wine, and it's possible it'll actually affect that next wine. So that's oftentimes why in with wine tasting and stuff, they'll give you like bread or crackers or something to eat in between. They always call them like palate cleansers. So this is the same idea. It has to do with research and carryover. Think about IQ. If I take an IQ test, it's likely my responses to the IQ test the first time, I might remember some of them. I might actually recall some of the things that I responded to or things, and that's going to carry over to me taking the test the second time and can actually impact the score. So I might do better the second time, not because of IQ Plus, but because I've already seen that test before. Right? So that's what carryover effect is. Subjects are no longer naive. So this happens a lot when you do repeated measures designs. A lot of research requires some, at least minor level of deception of the participant. Because if the participant knows exactly what it is you're doing or what it is you're trying to research, well, it's going to change the way that they respond. It's likely it may sort of bias the results, because if they know what you're looking for, they may try to give you what you're looking for, or they may be reactive and try not to do that or whatever, but it's going to impact the way that they respond. So by giving someone an IQ test, for instance, you may be cluing them in, they're interested in IQ. So the way that they respond, given the 10 days of taking IQ Plus, or doing the test the second time, may be impacted by the fact that they sort of are clued in to what it is you're doing. Same thing with THC. If you're having someone recall a bunch of words, and you give them some green Rice Krispies treats, right? They may sort of figure out what's going on. They're not naive anymore because I already got a recall task, and they give me a second recall task, and that actually may impede upon their ability to do that recall task, and it can affect the results. So that we oftentimes rely on participants being naive to what it is we're doing, and the more you do things to them, have them repeat tasks, the less naive they're going to become, and that can actually be a problem. And sometimes change may just be a function of time. This could be true even in our example where, we had participants do a recall task. Then they sat around for 2 hours. They did a distractor or whatever, and they did a recall task. Then it was like they ate some things and sat around for 2 hours. It's likely that, as it got later in the day, their recall could have just been affected by the fact it was later on in the day and they're more tired or whatever's going on. Their recall could have been diminished simply by the amount of time it took to go from the first recall task to the second. Time, if time's even further along, if you even get more time in between things, not necessarily in our example, but let's say I'm doing something like a math test. I'm looking across. This is what what schools do. They look across 7th, 8th, 9th, 10th, 11th grades at sort of these math aptitude tests, and you're looking at changes, and they might attribute that to the teachers or the school programs or interventions or whatever. But it's likely students are changing their math abilities simply because they're maturing. They're getting older and they're changing their sort of viewpoints and things, and they may actually be getting better at math simply because of time and has nothing to do with interventions or the teaching. So when change becomes longer, or the time interval becomes longer, there's even things that are issues with repeated measures like maturation and even other events that are occurring alongside or in between the pre and post that can actually affect things as well. And sometimes doing repeated measures designs is just not logically possible. There's just some things you can't do as pre-post. If I'm interested in comparing gender differences in math, right? Can't really do that as a pre-post test. All right, so everybody at pre, you're going to be male, and then you're going to come back and be female. Or I guess if you want to talk about gender, I want everyone to be men the first for pre-test, and then women for the post-test, and we'll see there's a gender difference. It doesn't make a lot of sense. You can't really do that. Now, there have been some interesting things where people have done tests where they're like, all right, I want you to respond as if you were the opposite gender or something like that. And they found that people actually do a fairly good job of trying to capture what that would work like on certain things. But that's not what we're talking about here. We're talking about people actually shifting their genders just at will to do a pre-post test, or change their ethnicity, or change your height. You can't really do some things as a pre-post test because it's not possible. You have to do them as a between subjects, independent samples sort of test. So the issue that comes down with doing significance testing just in general is that, so we figured out that our 3.6 mean, or difference in recall between pre and post was not likely to occur by chance, at least not relative to 0. Okay, so it has a less than 5% chance of occurring all by itself. But does that mean that it's a large number? Is 3.6 words a huge amount of recall loss? Should we be concerned about THC users and this dramatic loss of memory? So it's hard to sort of judge that based on significance testing all by itself. So oftentimes significance testing where we say, okay, this has a less than 5% chance of occurring, we need to accompany that with some other things like effect size, confidence intervals, something to sort of give people more information about just how impactful the study is. So here, the sort of raw effect is roughly 3.6. So there was a drop of, on average, of 3.6 words between the pre-recall and the post-recall. But the units of measurement have no particular meaning. Right? Number of words, it's sort of, right, is losing 3 words, 3.6, 4 words, is that a lot? I don't know. So we need to figure out a way to scale it, to figure out if that is a big difference or not. Is that a large difference? So we oftentimes will do that by, instead of, like with the t-test, we compare the difference to a standard error. Well, here we're going to compare it to a standard deviation to see just how many standard deviations, or what portion of a standard deviation people change from pre to post. And that's usually how we do effect size. Now, this is not me, this is how it typically is sort of put out there. I don't know why. But This is also referred to as D, which is I find super confusing. But so we have, like it says down here, capital D I'm trying to use to refer to the difference, right? The difference score. Right? D for difference. This D, as it says down here, that we're referring to in this equation, this D refers to Cohens D. And it's a standardized effect size that's pretty widely used in a lot of research and stuff, especially in psychology and social sciences. So that's why the D here is a reference to Cohens D, and more often than not, really, you'll see this written as Cohens D, and then they'll use like mu1, mu2. They use all population values, and as soon as you stick in the sample values like we have here, it's still D, but they usually refer to this not as Cohens D, but it refers to it as D hat. They put this little goofy hat on there. The reason why is this is considered, if you're doing it this way, theoretically, this is a parameter. This is talking about the population. This is an actual population parameter. What is the effect size in the population? Well, down here I'm not using the population values, I'm using the sample values. So this now is, when this hat thing, the little hat, this thing, right, tells you that something is a population, is a parameter, it's a parameter estimate. Where this is the actual parameter, like if you actually have the population values, the hat over something like this tells you that it is a parameter estimate. Okay, so oftentimes that's the sort of shift. We went from D, that's the parameter, to D hat, which is the parameter estimate. That's a lot of semantic mumbo jumbo, but just to sort of keep things clear, if you ever see these, that's sort of the difference. Most effect size, Cohens D effect size, has this sort of generic look. It's like we're going to take the difference between two means and we're going to divide by a standard deviation. Okay, so this could be sample population, two samples, whatever it is. We're going to subtract two means and divide it by a standard deviation. The trick here comes down to, well, which standard deviation goes in here? So if I go back a second, when we did the t-test, we focused on the difference standard deviation, this 5.337. And the reason why you don't see that number in the Cohens D is because when you're actually doing pre and post testing, the sort of general rule or general belief is that don't use this one, use the pre-test standard deviation. The reason why we use the pre-test standard deviation is because it's the one that's considered sort of unadulterated or unaffected by the study. So as you go pre to post, whatever you did to them that led to their post-test scores, it affected their standard deviation. They are varying less at post than they are at pre. Pre is really a measure of just their differences between people's recall. It's just a measure of individual differences in the variability between recall scores. So this is really the unaltered, unaffected standard deviation, which is why when looking at Cohens D, we use that one to standardize our effect size. So we're taking the standard deviation before, and we're going to divide it. So 3.6 divided by 5.855 is that 0.62, and which doesn't, by itself, isn't really super informative, except that, because 5.855 is a standard deviation, it tells me that the change in 3.6 words from pre to post recall is about a 0.6 or 60% the way to a full standard deviation. So it's not quite a full standard deviation change, but it's 60% of one. And the same Cohen who developed Cohens D also provided guidance in terms of what size things were. So I think I mentioned this in the last one, but I'll do it again. So if Cohens D is 0.2, it's considered small. It's a small effect. If it's 0.5, it's a medium, moderate effect. And if it's 0.8 or more, that's considered large. All right, so if you're able to, if the effect is 80% of a standard deviation or more, that's considered a large effect. So here, we're somewhere in between, right? Our 0.6 is somewhere between, you know, medium and large. I feel like all of a sudden I'm hungry for pizza. Anyway, so we're, you know, somewhere in between a medium and a large, and our 0.62. So this effect is sort of medium size, right? It's not quite at the large end yet, so we're of a medium size effect. Because we're able to sort of move it more than sort of a half of a standard deviation from pre to post, that's considered a medium effect. And what this relates to is as the effect size gets smaller, it goes this way, right? The effect size gets larger like this. You need more N. It requires more N, more subjects to find a significant effect. So the fact that this is a sort of medium effect relative to, say, the something like a 0.2, I'll need more subjects to find this effect significant than if it were a large effect, but I would need even more subjects if the effect was smaller. So this medium effect requires sort of a medium number of subjects. So at our 10, we were able to find this to be significant. So that was enough subjects to have enough power to find this medium effect significant. So difference is, again, 0.62 standard deviations, which is, it says a large effect. That's not true. I just went through talking about this is not a large effect. It is a medium effect. Right? It's a medium effect. And I mentioned before why use standard deviation before instead of the post or the difference is because, again, I mentioned before, because it's considered the one that's unaltered. It's a better representation of what this standard deviation might look like in the population for recall. So that's one we use. And also notice that we substituted statistics for parameters in the equation, which then changed it, again, like I mentioned before, from Cohens D, got changed over to the sort of D hat, technically. Right? So whenever we start to estimate a population parameter, we oftentimes will throw a little hat on there. And this is a little bit funky because usually with anything relates to the population, we typically use Greek letters. So you would expect something like delta or something would be, you know, Cohen's delta, but it's not. It's Cohen's D. It's one of the places where the convention of using Greek letters for population values and Latin letters for sample statistics is broken, right? So Cohen's D is a population estimate in its sort of form, and then it's D hat, which is our population parameter estimate using our sample statistics. But I wanted to say one thing so one thing you'll notice in the one sample test, the last part of that is we talked about confidence intervals, and I mentioned confidence intervals in the very beginning. And I left it off of the slide simply because the way you do a confidence interval for a dependent samples test is exactly the same as it is for a one sample. So just to sort of rehash that for a second, the confidence interval at 95% or whatever is going to equal the mean of the differences that we have. Right, it's going to be plus or minus. We're going to find our T critical, but two-tailed this time. Right? We want, even though we did our example as a one-tailed test, confidence intervals are always two-tailed. Okay, so we're going to find our T critical, that is two-tailed, 0.05. Right? We want all that stuff. Okay. Two-tailed 0.05 alpha T critical, and we're going to multiply that by the standard error we found for the mean of those difference scores. Right, so it's the T critical we're going to look up on a table times the standard error, and that's your confidence interval when it comes to difference scores. So to dependent samples test. So let's quickly look at that. Just so. Same thing, it's still 9 degrees of freedom. So can you see that? Okay, yeah. So we're going to go down to still 9 degrees of freedom. We're going to go over one column to the two-tailed test of 2.2622, 2.2622, 2622. So this is 2.2622. That's our two-tailed 0.05 T critical. And the reason why it's two-tailed is because for critical value, even though we did a one-tailed test, for the confidence interval, we want numbers that are above and below the mean at an equal distance. So that's the sort of two-tailed version of it. So we need our standard error that we found before, which I have quickly forgotten, but I think it's, let's go back for a second. Let's go back some slides and find out what it's supposed to be. So it's going to be 3.6 is the mean. It's going to be, it was back here. It was the 5.337 divided by the square root of 10. Okay, so 5.337 divided by the square root of 10 is that 1.688 value. Okay, so we're going to go back to, let's go back to the blank slide here, times our 1.688. Okay, our mean was 3.6. All right, so let's multiply those two out. I'll just say 262 to keep it all 3 decimals times 1.688 equals 3.818. All right, so this is plus or minus 3.818. All right. 262 times 1.688. Yeah, 3.818. So 3.818. And I'm going to take 3.6 and I'm going to add and subtract that from there so that our confidence interval should look like 3.6 minus 3.818 equals, so on this end you get a negative 0.218. It's going to be less than or equal to, okay, 3.6 plus 3.818. So the two are the mean, the difference here is less than or equal to 7.418, and that's the confidence interval. So the real mean of the difference is somewhere between here. Now, 0 is in there, right? 0 falls somewhere in here, which means that looking at it as a two-tailed test, we likely wouldn't have rejected. Okay, so but as a one-tailed test we did. That's what tells you the difference between sometimes doing a one-tailed test or two-tailed, and you can get a different answer doing a one-tailed test, and you might get different information when you do the confidence interval. So because 0 was in here, 0, you know, no change in recall is a perfectly logical population value for our sample given a two-tailed, the two-tailed specification here. Okay, so that wasn't included in the slides, and I figured that was worth sort of just going through, just so you get another idea of how it works. Give you an example of that. And that's it for dependent samples.